All right, welcome back. This is where it all comes together. Over 5 lectures, we have built the physics from the ground up, piece by piece. Now, we're going to look at where mammography is today, and more excitingly, where it's going.
Seriously, this isn't just another lecture. This is the capstone. We're about to connect every single principle we've learned, from the photoelectric effect right through to dose calculation, to the powerful tools that radiologists are using at this very moment, and the revolutionary tech that's just over the horizon. So, the first, and you could argue the most important leap, into the modern era was that huge shift away from analog film to digital detectors. And let me tell you, it changed absolutely everything. Now, here's a trade-off that might actually surprise you. Most people just assume, that digital won because it had better resolution, sharper images. But look at the numbers. Film was actually sharper. So what was the secret sauce? It was detective quantum efficiency, or DQE. The easiest way to think of it is as photon efficiency. And digital systems are just way, way better, about twice as good, at using the X-ray photons they receive. And that means you get better image quality for the same dose or the same quality for a lower dose. That efficiency, that was the real game changer. And this wasn't just some theory cooked up in a lab. The huge digital mammographic imaging screening trial, we call it DMIST, proved it in the real world. While overall the performance was pretty similar, in the toughest cases, we're talking younger women and women with dense breast tissue, digital was significantly better. And why? Because that superior DQE could pick up those subtle contrast differences that film just couldn't see. Okay, so digital was in. The next big hurdle was tackling the problem of overlapping tissue, when healthy tissue can hide a cancer in a flat 2D image. The solution? Digital breast tomosynthesis, or DBT, which lets us essentially see in slices. It's really a brilliant concept. Instead of one shot, the X-ray tube moves in a smooth arc, taking a whole series of low-dose snapshots from different angles. Then a powerful computer takes all that data and reconstructs it into a stack of 1 millimeter thin slices. It's really like being able to flip through the pages of a book instead of just staring at the cover. The radiologists can just scroll right through the breast tissue, layer by layer, and see details that would have been completely hidden before. In the results in the clinic, they're undeniable. Tomosynthesis finds 20 to 40% more invasive cancers than 2D mammography can on its own. It just sees more. It's that simple. But here's the other side of that coin, and this is just as important for patients. It also slashes the number of false alarms. Those stressful callbacks for what turns out to be nothing? It reduces those by 15 to 40%. That means a whole lot less anxiety for patients and a much more efficient system overall. Now, at first, Tomo came with a bit of a dose penalty because you had to do the 3D scan and a regular 2D image. But then came another fantastic innovation, synthetic 2D. This is just really clever software that creates a traditional-looking 2D image right from the 3D data. And just like that, the whole exam became dose neutral. That's what really cemented tomosynthesis as the new standard of care for screening. Okay, so tomosynthesis gives us anatomy in 3D. Amazing. But what if we could also see physiology? What if we could see blood flow, which, as we know, is often way higher in cancerous tumors? Well, that is exactly what contrast-enhanced spectral mammography, or CESM, does. This is just beautiful physics in action. So you inject an iodine-based contrast agent, and then 2 images are taken, one right after the other. One at a low energy, just below something called iodine's K-edge, and one at a high energy, just above it. By subtracting one from the other, the computer can magically erase all the normal breast tissue and show only the areas where that iodine contrast has pooled, highlighting suspicious areas of increased blood flow. It's so clever. So where does this fit in? Well, you should think of it as a really powerful, super accessible alternative to a breast MRI. Now, MRI is still the gold standard for sensitivity, no question, but CESM is way faster, it's cheaper, and you don't have to deal with issues like claustrophobia. That makes it an incredible problem-solving tool in so many clinical situations. Right, so we've gone from film to digital, from 2D to 3D. We've even added a functional layer. What's the next logical step? Well, it's the revolution that's happening right now, adding a layer of intelligence with artificial intelligence. This is so important to get right. AI is not here to replace the expert human radiologist. It is here to augment them. I want you to think of it like an incredibly sharp, incredibly vigilant co-pilot, helping the radiologist be faster, more consistent, and more accurate. But the final decision, that always, always rests with the human expert. And AI is being woven into the entire workflow. I mean, it can act as a tireless second reader. It can triage cases to bump the most suspicious ones to the top of the reading list. It gives us objective breast density measurements. And it can even help predict future cancer risk just by looking at the image itself. It's amazing. So where do we possibly go from here? Well, the next giant leaps are happening on two fronts. Even more revolutionary hardware and a much, much smarter, more personalized approach to screening itself. You know, if that jump in DQE from film to digital was a revolution, then photon counting is the next one. Instead of just adding up all the energy that hits a pixel, these new detectors literally count every single X-ray photon, one by one. This basically eliminates electronic noise, pushing DQE up to an incredible 70 or even 80%. And what does that mean? Even better image quality at even lower doses. This also signals a really fundamental shift in philosophy. We're finally moving away from a one-size-fits-all, age-based screening model. The future is all about using every tool in our toolbox, genetics, AI-based density scores, image-based risk models, to create a personalized screening plan for every individual. We're moving from a reactive model to a predictive one, where high-risk women get more screening and low-risk women get less. It just makes sense. And that brings our entire journey full circle. You see, all of these incredible advancements are built on a set of core, foundational physics principles that we've been talking about this whole time. And really, they all boil down to these 10 key ideas. The first few are about the basic physics, the right energy, essential tools like compression. Then, number 4, the principle that drove the entire digital revolution. DQE is king. Photon efficiency is what matters most. After that, it's about the clinical impact. We saw how tomosynthesis, number 8, improves detection and cuts down on those stressful callbacks. Number 9, how CESM gives us that functional layer, showing physiology, not just anatomy. And finally, number 10, the principle that's guiding our future. AI is here to augment, to empower the human expert, not to replace them. These are the pillars of modern breast imaging. And of course, mammography doesn't exist in a vacuum. It's part of a much larger toolkit that includes amazing technologies like ultrasound and MRI. Each one has a very specific role, but they all work together towards that one single goal: finding cancer as early as we possibly can. And this really brings us to the ultimate vision for the future. We've spent this entire series on the physics, on the how, but the future isn't just about better detectors or cleverer X-ray tubes. It's about combining that brilliant physics with a layer of powerful intelligence, where every single piece of the puzzle, from the photon leaving the tube to the algorithm analyzing the pixel, is all dedicated to one unified goal: finding cancer earlier. Thank you so much for joining us for this comprehensive guide to mammography physics. It has been a pleasure. It's such an incredible and dynamic field, and honestly, we're just seeing the beginning of what is possible.